Good evening, everybody. I think it's 5:30. So, welcome to the Southwestern Centre of the IMechE Railway Division. My name's Matt Prosser. I'm the chair of the Southwest Centre, and welcome to our second virtual lecture of our 2021 programme. We are trying a new platform this evening, rather than one that we used a week or so ago for the chair's address, and it has the advantage of having a webcam facility. So hopefully you should be able to see me, and you should be able to see our presenter tonight. So makes it a touch less impersonal than it was before. So welcome everybody. Now tonight's lecture is by Nasser Majothi, Director of WSP Rail, and continues our theme of railway systems. And Nasser will be talking about systems integration and systems engineering. Before I hand over to Nasser, there is a chat function to ask questions, so please fire your questions in as we're going through, and at the end of the lecture I'll pick those up and put those questions to Nasser. So if everybody could stay on mute, you do have ability to speak, I think, with this WebEx function. So if you could stay on mute, that would be brilliant. So without further ado, I'm going to hand over to Nasser for the lecture. Thank you. Over to you, Nasser.
Thank you, Matthew. Just double check you can see my screen and hear me.
Yes, I can. Yes.
Good. Thanks, guys. Yeah, thank you, Matthew, Mick, Fiona, and Prasad for organising this and inviting me to speak to you. It's really nice to join you, and always a pleasure to present to the IMechE. I'm a chartered mechanical engineer myself, and I've been attending these events for many years, and it's good to be presenting at them as well. So I'll just introduce myself, tell you a bit about myself, and then I'll get on with the lecture. I'm a chartered mechanical engineer by background. I've been working for around 20 years, mostly in the railway sector, although I've done some time in IT and automotive, but the vast majority of my time has been in railways and transportation, both in the UK and outside of the UK. And I spent most of that time either doing design engineering, program management, or systems integration. So that's the kind of primary focus of my presentation today, and that's my technical background as well. Currently, I work for WSP, and I'm seconded to HS2 as the head of systems integration. And what we're talking about today is really big systems, so infrastructure systems primarily, and how systems integration is applied to infrastructure. So I appreciate many of you might have other backgrounds and other sector experiences where you do systems engineering in other ways, and I'd love to hear about that in the questioning. But I'm really focusing around railways, infrastructure, and how systems integration is applied to that. It's been quite a hot topic in the industry over the last decade, and certainly in the last couple of years with Crossrail and other big infrastructure projects going on with this. Hopefully it's very topical, and you'll find the content quite interesting. Presentation is about 5 minutes, and I think we've got a good amount of time for questions at the end as well. So my presentation is going to be in two parts. The first part is really just answering the question, what is a system? So just kind of lay the foundation of how we describe systems, what systems are, the environment within which systems exist, and some of the risks there are inherent in developing systems. And the second part of the presentation, I'll talk about how we manage the development of systems, and what I call complex systems, because major infrastructure projects are invariably complex, and I'll define what complex means, and the types of processes and tools that you can use to manage systems engineering projects. But I'll also talk about the people side, the management and the leadership, and the kind of things you need to do to lead a team in a complex environment. So there are two parts of the presentation. One is what is the system, and the second is really how do you manage in that system's environment. So we're straight into what is a system. So I'm going to go through a broad definition of what a system is, and hopefully by the end of it you'll have an understanding of my perspective of how I'm thinking about systems and applying them to projects. It's not a new concept, systems. It's been around for a long time. You probably recognise this chap as one form or another. This is Aristotle, a Greek philosopher from more than 2,000 years ago, and he's attributed with the maxim that is probably familiar with everybody on the call: the whole is greater than the sum of the parts, which is a maxim that we all work with. It is kind of every day. But that's not actually the quote that Aristotle made. That's not right. And I've provided two paragraphs there on how he was actually thinking about systems. And it's surprising that such a long time ago, Aristotle and probably his other contemporaries were thinking about systems in quite similar ways to we think about systems today. I won't read the paragraphs in full. I'll just highlight a few elements. The totality is not, as it were, a mere heap, but the whole is something besides the parts. So this understanding that parts have to come together to make something bigger, and they deliver something else, some other such quality. So there's an output to these parts of a system that is somehow greater and is some kind of quality. And of course, we talk about quality in our systems and engineering all the time. The whole is not the same as the sum of the parts. So it's this idea that when we put the parts together, you do get something different. You get something extra. And then he goes on to talk about the process. What is the process of putting the parts together? And he says, even when the process is clear, perhaps you still don't get what you intended. So you may have the parts, but you may not get the whole. Is part of this philosophy. And this is very similar to how we think about systems today still. So we think about parts, we think about processes, and we think about what is the outcome of this system. So this idea of systems is really quite ancient, and I will show later in the presentation some of the development of that thinking around systems that we actually use in managing systems engineering projects. So as a simple example of a system, I ask the question, is a car a system? And you know, it's a product that we all use very frequently, or probably every day, but thinking about it as a system actually is quite interesting. So a car as a set of parts, is that a system? Well, when you design and build a car, you develop lots of components. Those components are optimized for that car. You couldn't change the engine of this car, which is a Volkswagen, for the engine of a Rolls-Royce. It wouldn't work. It's not designed to do that. So this idea that you develop lots of parts that are optimized with each other, that is part of systems thinking. But also that those parts need to come together as a product, and a product is a system itself as well. And you could apply this same thinking to any type of product. A set of optimized parts becomes a type of system. So a mobile phone, or a computer, or a heating boiler, or whatever. Lots of parts optimized and designed to work together to deliver a product. So we think of products as systems as well. But actually that product is for an end user. And an end user has to interact with the product in different ways to make it function and perform as intended. So in this case, in this older type of car, the end user is a driver who needs to change gears, press the accelerator, press the brakes, steer the machine. There's only a system once the end user gets involved. And that product and those parts are designed for that end user, and that's what we call requirements. So the requirements of the system are fundamentally around how does an end user use this particular product. But it's not really a system until you start thinking about the end user and the product in terms of a context or an environment. And the environment for a car is obviously a road. People do take cars off-road as well, and that is a particular type of product, type of car, an off-road car. But in this context, it's a car to be used on a public highway. And that is the infrastructure that enables the end user to use the product. So all of that together, in my mind, is a system. A context and an environment where the system can be deployed. An end user that uses, operates, or maintains the product. A design product itself, which is the sum of optimized parts. So to answer the question, yes, the car is a system, but only when you think about it in the wider context. And the context is broader still. So the car and the highway and the driver are part of the wider transportation system. So that is one of the infrastructure systems that we as a society have developed. But those transport systems can't be delivered without a reciprocating manufacturing system. So we need manufacturing to be able to build the car or the train or the aeroplane. And in itself, the manufacturing system, again, is a set of design products and contexts to enable that to happen. It also needs some power and some energy. So we have an energy system, and it might be petrol, or it might be an electric car, but all that requires some level of infrastructure to make the car, to power the car. And beyond that, modern cars, they've all got sat-nav, so we need a communication system to communicate with our car back to the satellite so we can navigate, and so on. The commerce system enables us to buy the car or finance it. A logistics system enables the parts of the car to be delivered when you need it maintained. The internet, a ubiquitous system, is a part of all our systems these days. Talk about the food system, or you know, the farming system, and our transport system may be utilized to deliver food. Might be one of the end users of our transportation system. The government sets rules and regulations to enable us to safely use our cars and driving, like the taxing and licensing system. Various other systems, infrastructure systems, that are part of enabling our transport system to work, and vice versa. All of these systems work together in some level of harmony that we've designed and built. And we call that the system of systems. And that is a concept that lives really above the product and the system level. So this is the world that we have designed and built, and we call it academically, we call it the system of systems. But it's not really just an academic concept. It's really the context within which everything that we design needs to work. And all of these other systems, somehow they put requirements onto the product or the system that we're attempting to design. And this really comes into play every day. When you're delivering an infrastructure project, this concept of system of systems is actually really quite important, because all of these other aspects, or all of these other systems that you interact with, they all have standards, they all have their particular norms, they all have their different supply chains, and they all impact how you're going to design and develop your system. And as an example of this, this is a real infrastructure project. This is the Boston Big Dig. It was completed in 2007, and there was a lot of controversy around this particular project because of the amount that it cost and the delays. But essentially, it was a transportation project through the heart of Boston, and the purpose of which was to improve the transport flows through that city. And as you can see there, just in the lower left-hand side, you can see part of that project being built. And as you can imagine, in a project like this, through the centre of a major city, all of those systems of systems come into play. So you're building a new highway. You've got to interact with the buildings around you. You've got to interact with utilities, energy systems, etc., to make this particular project work. So this idea of system of systems as placing a constraint on your system of interest is really quite important, and is the reason why our mega projects, particularly in transport, cost so much money, because actually they're not standalone things. They're part of a much wider environment that you have to alter or work within to build the project itself. This is the finished article, and as you can see, it looks almost the same, but not quite. Where that road was, you now see a public space that is rather nice to look at, with some green spaces, etc. So really, that infrastructure system has transformed this city, and from what I understand, the actual transport benefits have been really significant. So it's worth asking the question with these type of mega systems: what is success? We see problems and delivery issues with these projects all the time. And while they're being designed and built, they're often quite late, and they often cost more than intended. But quite often, they deliver significant benefits to cities, to populations, and really the measure of success is over quite a long period of time. So this project now is actually seen as a success. So that's the idea of systems of systems that must be considered in your overall context in delivering your particular system. In this case, it was the car. So we get consequences from our systems, the things that we developed, both good and bad. And in the case of a transport system, you get a variety of different benefits. So I put them down here. The benefit of a transport system, obviously, you can travel long distances, which you couldn't before. You get food security from our systems. You get, through our medical systems that we develop, longer and healthier lives. And as we've seen over the last maybe 20 or 30 years, global connectivity and commerce. So the benefits of this system of system that we've created and the products within that are really quite profound, and they are the building block of the society that we live in today. This idea that we can take needs of the population, turn that into requirements, and turn it into functioning products within a wider infrastructure is really quite profound, I think, and is one of the most important inventions in terms of our ability to do things that mankind has really. But these systems also come with some pretty big consequences as well, and not all of them are immediately obvious. Health and safety risks. So that's a thumbnail picture of Chernobyl, a system that went badly wrong about 30 years ago, I think, slightly more than that, maybe just 12 years ago, and devastated a whole area. And about 50,000 people had to be moved, and I'm sure significant loss of life as well. The health and safety risks are a significant consequence of developing complex systems. The more complex the system is, the more ways in which it could go wrong and will be affected by its environment. So understanding the risks, the health and safety risks of the systems we are developing is really quite critical. There are bigger consequences as well around populations. So all the benefits of the systems we create actually are quite attractive. And over the last half century, we've seen rapid urbanisation. That is because our cities, which are full of these systems and system growth systems, are really quite attractive. And you know, we've seen rapid urbanisation because of it, with the benefits and the problems that brings, and that really is a global trend. Environmental problems are also caused by our systems. If you take these consequences actually happen over very long periods of time, and are very incremental and not very noticeable either until perhaps it's too late. And you know, as we've seen with climate change and loss of habitat, a lot of that is because the systems that we have are actually very efficient at doing what we do. So getting oil out of the ground and burning it is something that our infrastructure systems do very, very well. But over many years, the impact has been really quite significant and is changing our planet. As an irony to that, perhaps the design of new systems are the solution to that as well, and indeed in turn those systems will come with their own risks and consequences as well. So there is a real moral element to this, and the role of the engineer in society really comes to the fore when we think about big infrastructure systems. What are the opportunities and risks that the systems we design bringing out? What are those consequences? And as we design systems that are more and more complex, we really, as engineers, we have to take that into account and understand the long-term impact of the things that we are designing. And I'll just talk about the railway as a system, and talk about the kind of things that I deal with in my job. So I'm sure we're all familiar with the basic subsystems of a railway, the train, the rolling stock, which is a product and should be designed as a system in its own right, but that interacts with other parts of the infrastructure, tracks, the power, signaling, communications, mechanical and electrical systems. So they're the kind of visible technical elements of a railway that need to interact to deliver a working railway. On the civil engineering side, which by the way is about 80% of the cost of the railway. There are stations, people can get in and out of the railway, depots for sailing trains and things. There's a large number of buildings that you need to house various things. There's the line of route, which includes embankments, tunnels, bridges. Also quite a lot of highways involved with railways, and of course lots of utilities that either interconnect with the railway or cross it. So we've got both systems and civils really interacting quite closely to enable a railway to be built. But then there are lots of cross-cutting system issues or transverse requirements, we sometimes call them, that the railway either needs to deliver or work within the constraints. So we've talked a little bit about the environment already. So railways are overall net positive effects on the environment, a very efficient form of transport, but actually building a railway has significant environmental impacts. So a core requirement is to minimise that environmental impact. Similarly with safety, there are hazards involved with delivery of a railway and indeed the railway in service, and that's why we have a signalling system. So safety is a key system-wide consideration. Performance and functionality. What performance do we want out of this system? How many trains per hour? How many passengers do we want to move? How does the railway work in terms of functionality? How do operators actually use this system? RAM, reliability, availability, maintainability. That's a core requirement of the system. How reliable can we make this system? How much money do we want to spend to have a reliable railway? Noise, particularly difficult to manage. Lots of sources of noise from a railway, both for the passengers and the staff, but also the neighbours of the railway as well. So we've got to look after our neighbours and manage the noise emissions from our system. EMC or electrical integration, which includes anything as well. Again, a complex interaction. The railway produces lots of electrical interference, which we need to manage. I've got highways there twice. But ergonomics, how do people interact with the system? You can see there the platform train interface. Critical managing the interaction between passengers and the train, both safely and in terms of performance. But people interact with railways in many, many different ways, and we've got to design that interaction into the system. Railways have a huge number of stakeholders, and all of these stakeholders put requirements onto our railway, and things that we have to do. So the roles of the railway, passengers, operators, maintainers, the people, the neighbours I've already mentioned, security, so that's the police. There are security requirements as well, such as cyber, emergency services, local government, national governments, lots and lots of stakeholders involved in railways, and that is true of many infrastructure linear systems which cut across a really large geography. So as you can see, it's a pretty complicated picture around developing a railway system, and the technical aspect of it is only a small part. You can imagine all of these elements interacting with each other as interfaces, and we have to manage all of those interfaces to deliver our product. So what is that product? What is the product of this complex system? Well, I'll put it to you that it's actually the timetable, and delivering the timetable service is really our product, our offer to our consumer, the passenger. And if we do the system right, we can deliver that timetable at an affordable price, and deliver the journey in a comfortable manner. So as developers of a railway system, we must always keep in mind the end goal, which is that timetable offer to our consumers. So just to wrap up on this section and just answer the question, what is a system, and recap on all the things that I've said. A system is a collection of parts that interact in specific ways to form a product system. A system has end users who interact with it to perform some useful function. A system performs as part of a greater context, which includes other interacting systems and also the environment. A system will have both intended and unintended consequences. And finally, engineers must recognize and address both the opportunities and risks that their systems bring. So that's my definition of a system. You probably won't find that in a dictionary, but that's kind of my view over my experience of how to think about a system. So just moving on to part 2 of my presentation, which is really about how you manage the delivery of complex systems. And this section really reflects what I do on a day-to-day basis as a manager of a systems integration development right now. And we'll continue with the railway example as a way of illustrating the methods here. So the first thing is to recognize that not all projects are the same. So not every project is highly risky or highly complex and needs a full-blown systems engineering methodology. I would argue that all of them need some type of systems thinking. You must always think about your end user and the environment within which you're delivering the system. But not all of them need the level of and depth of systems engineering management always. So I've got a bit of a scale here of transport projects, ranging from a cycle path to the ultimate transport project, which would be getting man to Mars, or woman to Mars. And obviously, delivering something like a cycle path is relatively straightforward, not very complex, not particularly risky, and requires minimal system integration. A motorway, or perhaps a smart motorway, would become an intermediate level. Motorways themselves are getting a lot more complex with the invention of smart motorways and autonomous vehicles, and I'm certain we'll see the highways sector doing more and more systems engineering in the near future. Railways and metros and public transport systems are really quite complex, both legacy and new railways. Part of that is because of the technology and the highly coupled nature of the engineering. Part of it is because of the safety criticality. With being public transport systems, the safety requirements are really quite stringent, and so that means the needs of a systems approach is quite phenomenal. But also, there is a layer of new technology appearing, particularly on railways, that has to be integrated with legacy technology. So that makes railways and metros really quite complex and quite risky. And in the top corner there, I've got really that's a kind of an R&D space, or a space where you're doing something really quite unique, and it involves quite a lot of basic science as well as engineering. And I don't get involved in that in what I'll do, but there are plenty of projects out there that take this kind of systems approach, but to a much higher degree. So these systems approaches, or these projects, don't always go to plan. This is the Elizabeth line, also known as Crossrail, and I believe this image is from 2018, I think, where they had a ceremony to actually inaugurate the progress on the line and rename it the Elizabeth line, and quite rightly, because it's a huge piece of infrastructure and right to celebrate that particular achievement. But since then, things haven't quite gone to plan, and I really don't want to criticise what's happened on that project because these really are difficult, complex things to achieve. But it's got the national headlines. The program is going to be late. It was on the news and the TV and the newspapers, and various reports written, including this one to the House of Commons in 2019. That concluded Crossrail Limited had underestimated the challenge of systems integration. Crossrail, even since then, is not delivered yet, and still tackling those systems integration challenges. So earlier in the presentation, I said civil engineering is probably about 80%, 70 or 80% of the cost of these projects. The system side and making the system work as a functioning operational system for the end users is probably about 20% of the cost, and that includes the running stock as well. But that is not, the risk of the project is predominantly in that system side, even though the cost of it is significantly less than the civil elements. The risks are really quite significant in that end of the project, and I'll particularly mention software because we're moving into a world, or have moved into a world indeed, where software is integral to almost everything that we do. Developing software is a normal part of the engineer's job now, and I would say that the infrastructure sector has not quite caught up in terms of understanding that software is integral and a core part of delivering any mega project, and that has been one of the problems on Crossrail, I understand, and something that I believe that they're still trying to address. Due to these problems, there has been quite a lot of investigation, reports, lessons learned on how we deliver these projects better. And I've done a personal study going back about 10 years of all of these reports and many others that look at how we deliver infrastructure projects better, and quite universally they point to a need for better systems integration as a theme, and a few of these reports are well, most of them around railways, but a few from other sectors as well. But I think the lessons are pretty universal, and I've kind of summarised them here. And not many of them are technical actually. Once you kind of look at all of these lessons, you see that actually a lot of them are about how organisations work. So culture comes up quite often. Having a culture of thinking about the system and making sure that it's everybody's job to deliver an integrated system. Leadership comes up quite often. So visible leadership. Are the leaders of your program championing integration? Are they championing the delivery of the system and not just assets? Focusing on the end state, and by that I mean the operational system, the end state railway. Is everything that you do working towards that operational end state railway? Because if it's not, you're probably not doing good systems integration, systems engineering. Having clear accountabilities is really important. So pushing down the process and the accountability for systems integration down into the supply chain doesn't always work. The client or the owning organisation has to keep a really clear responsibility for leading systems integration, and where things are pushed down into the supply chain, having that really clear in contracts particularly the interface, is what is expected of those contractors and how they need to work together and what risks we expect them to manage. Allowing time for integration. A lot of integration happens in the design phase. So if you design a good system, you have a good chance of doing system integration. But also in the testing commissioning phase. So allowing plenty of time in testing and commissioning and off-site testing as well to make sure all the integration is done before you bring your subsystems and parts onto the railway is really important. So planning that and running time for it. Understanding technology development risk, and I mentioned software already. But on every project, on every system, there'll be certain things which are proven and other things which are new products, new technology, and indeed some things that may require some research and development. Understanding those risks and where you have technology development to do and planning that in properly is really vital. And the final point there is around change. So change does happen all the time on these big infrastructure projects, but all change affects the whole system, and some to a lesser extent, but some to a greater extent. And it's not always obvious how that change might impact that end state railway or the end state system. So keeping an eye on change and understanding how it cascades through the system is really important. So now I'm just going to go through a really high-level description of the systems approach. So what you see on the screen here is really how systems work. So different parts and components interacting in myriad ways within some kind of boundary or context to deliver an output. But actually, to be able to deliver a system, we need to organize it in some way. So we go from this systems view to really this reductionist view, and that's where our problems start really. But it's a pretty unavoidable problem. Our tools at the moment really require us to do some kind of system breakdown, and you might know it as a work breakdown structure or a system breakdown structure. But we've got to go from this concept of a system to something that we understand and we can actually deliver. So we start this process back with our end users, so beginning with the end in mind, and we define requirements. You've probably heard that term before, but we spend quite a lot of time upfront in the project just figuring out what is it that we want, and write that down into a basic set of statements, which we call requirements. That leads to some kind of concept design, where we prove the feasibility of delivering those requirements, and we have some kind of organization that we set up to deliver the system. We then decompose the system into lots of parts and subsystems. A very simple representation here, but on a system like a railway, there'll be hundreds, thousands, tens of thousands of parts that we need to decompose and organize for delivery. And then we go into contracts for designing and building. Our requirements are packaged up commonly now into a database, which are then written into contracts and put out to multiple suppliers on a big project. It may be many dozens of suppliers that deliver various elements of the system that you then have to put back together. And that is where integration comes in. We decompose the system, but then someone has to put it back together and through the build and through testing and commissioning, we prove that the system has come back together how we intended it to. And at the end of it, we assure all of that to prove that we met those end user requirements, and quite commonly to our stakeholders and regulatory bodies say that this is what we intended to do, this is what we built, this is how we did it, and we can provide you with the assurance to say that this system is fit and safe to operate and bring into service. So in a nutshell, that is the systems approach. And as you can imagine, in a process sense, that has been standardized. ISO 15288, for those of you that want to look at the standard, that is for systems and software engineering. And essentially, that standard talks about all of the different processes that you need to do a systems engineering project, and that applies to all kinds of projects, be they infrastructure or manufacturing or IT systems. There's a generalized set of processes which we've now kind of arrived at. But unfortunately, taking a standardized approach to something that is so complex is really quite difficult. And we're in this world where we have lots of different components and products coming together. All of them have their different life cycles. The life cycle for developing software and processes for that is quite different to the life cycle of developing civil infrastructure, is quite different to developing a safety critical product. A lot of these life cycles are run concurrently, and so we have this quite difficult problem now of multiple life cycles run by multiple organizations over concurrent timelines. And so a really difficult problem in terms of actually executing what looks like a relatively simple systems engineering process. For those of you that have worked in railways, you'll have seen lots of different life cycles. Network Rail, for example, used the WIP life cycle. If you work in stations projects, you might have seen the REBA life cycle. If you work more on the safety side, you might have seen the life cycle in EN 50126 standards. So again, complexity to how we think about and organize our projects. And each sector, it has its own way of doing things. It's got its own standards, it's got its own approaches, and actually we've got to respect that and work around it. It is really quite difficult and probably not optimal to standardize our approach entirely. Industries that are built up over a long time, for example, building services, they will have a certain life cycle and a certain way of working that works for their sector, and that is proven. And somehow we've got to integrate that all back into our overall system life cycle project. So there are ways of dealing with this type of complexity, and I'm just going to give you a timeline of some of the ideas that I've come across, and indeed you've probably come across quite a few as well, different ideas of managing things that are useful as guidelines and pointers to managing complexity, and they can be used in any field, but I'm using these to manage in the environment of a major infrastructure program. So there's this idea of systems thinking and how organizations work, and that's really important. And I talked to you earlier about philosophy, and philosophy talks quite a lot about thinking about systems. But over the last 100 years or so, we've seen approaches to multidisciplinary working. So in the middle of the century, there was this idea that multidisciplinary teams could work on science and technology and engineering projects. Similar approaches then appeared in biology, thinking about biology systems. In the 1980s, approach a mode called soft systems methodology. And that's really quite useful in terms of thinking about people and organizations and stakeholders as part of your system. And then a couple of best-selling books on learning organization and how teams work have really influenced me in terms of thinking, well, how do you actually manage in these complex environments? There's a long history of systems engineering projects. Systems engineering as a methodology goes back about 100 years and primarily from the US. And the first ideas around that came from the Bell laboratories in the 1930s. But it really came to the fore in defense and missile programs, and probably the most famous mega project of them all, which is the Apollo space program. And if you read about that, you'll see that they use systems engineering techniques that were really recognized today. And that was a really watershed set of projects in the 60s and 70s, which really set methodologies for how we do systems engineering. And various societies have come up. IMechE, International Council of Systems Engineering, is a society now that provides a huge number of resources around how to do systems engineering. Agile development I'll come on to later in the software arena, and I just talked about the standardized 15288. So we really have a good pedigree in terms of systems engineering process, which is now quite standardized. But I also think manufacturing is a really good source of thinking about how to manage complexity in the way that they have approached and standardized the techniques there. Starting all the way back with scientific management, the Ford production system, mass production in the early part of the century, quality management, which is really key, and later in the time there, lean manufacturing, agile projects, and digital engineering, which we're embracing and trying to make core to that system development approach. So you can see that there's kind of, apart from the standardized approach I talked about in 15288, there's many influences and there's many ways of managing complexity, but really we've got to think about people and have a much more human-centric and team-centric approach to managing systems projects, which is what I'm going to talk about to conclude my presentation. So what kind of things as a leader on a project doing systems engineering do you need to think about? Well, integrating real legacy technology, that's a real source of complexity. Delivering your railway into an in-service network, are you integrating back into Network Rail or back into TFR, real problem. Huge number of stakeholders with competing or incompatible requirements. Long planning horizons. These programs go on for a long time. Developing an infrastructure system or railway might go on for 10 years. But at the same time, you've got to think very short term. What are you doing today to get to that end point? Really quite difficult to think about. Lots of external forces, not least things like what we're going through at the moment. Over such a long period, external things will happen. Multi-layered organizations, dozens of suppliers, lots of people interested in making decisions on these projects which we have to navigate. Numerous contracts, lots of interfaces, and lots of collaborations between lots of technical specialisms. So, as a kind of a nutshell, they're the kind of things, and I'm sure we could think of a lot more, but they're the kind of things that as a manager, you're having to deal with in delivering a systems engineering process. And as you can imagine, individuals and teams struggle to cope with this type of complexity. So I've come up with some rules of thumb that can be used, and hopefully that'll be a good takeaway for you guys. So think about the team, open the dialogue, control what you can, visualize to manage, create alignment, have a route map, and be agile. And I'll just quickly run through each of these. Teamwork. So there's not much you can do without teams. You have to have that team approach in these complex environments. You've got to plan for that coordination. Spend time developing effective meetings. You must have high competence and highly skilled people in the teams. Take time to understand the specialisms and integrate them in, but be aware that there's a huge cost of collaboration, because it takes a lot of time, money and effort to do collaboration, so you've got to think about it quite carefully. Opening the dialogue. So you have to have a structured, this is me working with my team here, and you have to have a structured dialogue in terms of dealing with these complex issues. You can't just talk about it and hope that it will work. Actually, you can have some structured approaches to talking about these things and capturing them and turning them into real plans for delivery. So I say it's not really just talking, it's about structured ways of exploring difficult, complex topics. Part of the leader's job in these systems environments is to be the leader of the dialogue. What are we talking about? What are the right things that we should be talking about? And using simple tools like the cause and effect diagram that's on the screen there. Listen, talk, and think as a team. So going back to that team ethos, but building this up as a team. Control what you can. So I talked about risks earlier. This is really about risks. You really need to understand what your important risks are and manage those. But there are lots of other things going on as well, lots of other things that are outside of your control. And working in systems integration, you can't control everything. So you've got to really focus on those system level risks that you can manage and delegate or monitor or influence on the other ones. Visualize to manage. So drawings and diagrams are essential. Otherwise, you can't really communicate what the complexity is and how you will manage it. Because picturing what this diagram are used on previous projects, and it really brings to life, like, what are we dealing with there? What needs to be managed? Where are the risks? Especially important when we're dealing with invisible things. So the software is largely invisible and will get forgotten. So you've really got to spend some time visualizing these things to be able to manage them. Creating alignment. Operations, technology, projects, contracts, they all have to be aligned around that end goal, and there are ways of doing this, different breakdown structures that need to be coordinated around some common goals to deliver that infrastructure capability or output, or whatever it is that you are aiming for at the end, and then having your people, teams collaborating around that alignment. And it's really important that all that gets into contracts. You will not get that alignment unless your requirements in your contract to deliver these projects have systems integration built into them. Simplifying schedules. I'll call this a route map, but really what I'm talking about is simplifying schedules so people can understand what their part in overall delivery is. And I'm sure you've all seen really big schedules built in Primavera or other such tools that are thousands of lines long, and you really don't know where you fit in. So it's important on a big railway project to simplify that and create a route map so that everybody's interaction towards achieving that end state goal is really clear. And you can simplify really quite complex schedules into a map just like this one. And each one of the milestones on this map the configuration of the railway. It says who's involved, what they need to do, and each one of these points delivers some element of capability that delivers the operational outcome. So it's really focusing everybody around the operational output. So it's really key to create that simple route map, common plan between all the delivery agents, having common milestones and clear steps that deliver that operational system. Being agile, you've got to move with what's going on with the projects. Things change and you have really quite difficult problems to solve in the middle of that overall system delivery. So you've got to stay agile, and by that I mean doing agile projects. And this is a kind of example of how you might manage an agile project. But within the overall delivery, there are always things that need solving, and using an agile project approach to pick out and pull out those problems that seem intractable and that have been going on for a long time. You can use different techniques such as agile project management to solve those things. So that's the end of my presentation. I'll just kind of conclude quickly. So I think we've shown that there is a need for systems integration, systems engineering for managing complex projects. In my mind, the future of systems integration is more a human-centered approach, understanding how people work together to deliver these systems, and leaders can take specific actions to manage complexity. It seems daunting, incredibly difficult, but actually there are things that you can do to make these systems projects more likely to be successful. And finally, when the slides are distributed, I've given a lot of reference material that you can go and look at your leisure. So thank you very much. Thanks for your time. Hope it was a useful and interesting presentation. I'll hand back to Matthew. Matthew, I think you're on mute.
So I am, yes, sorry about that. Thank you very much for that, Nasser. So time for questions. We've got some questions coming in on the chat pod, but please, if you have any questions, type them into the chat pod and address them to the panelists. So first question here from Andrew Skinner, which is clearly railways are a very complex system with many interactions and stakeholders. From your perspective, accepting your slide on the main lessons, what one thing should we be doing differently to manage safety and risk, particularly at the interfaces?
I think it's about clear accountability. So, we do spend already a lot of time identifying interfaces and how things are managed there. But accountability in the delivery has to be really, really clear. So, who is doing what? And that's much harder than it sounds, but we're necessarily getting that into contracts as well. So I think that would be my single biggest thing that we could do.
Okay, that's yeah. I mean that really was the question that I was going to ask, which was what is out of your list of the main lessons there, what is the single biggest one you think that will make the biggest difference? And I think you summed it up there with accountability. So I mean, what do you think, as a follow-on question, Nasser, what do you think are the biggest sort of systems challenges we have at the moment in terms of the railway? You had the Crossrail up there as an example. Are there any example? Is there anything that you want to particularly highlight from that project as a particular issue that's caused a lot of delay?
Well, I'm not involved with Crossrail myself, so my experience, my knowledge is just from what's in the media and and what a few friends and colleagues have told me. So it'd be unfair for me to use that as an example. But I can give you my view on the kind of things that need to be thought about and that are kind of significant risks. Hopefully quite a lot of that came across in the presentation. But managing the invisible things I talked about, and I still don't think that we've got good enough handle on software in this domain, and the benefits that it can bring, but also how to manage it. We don't have the cadre of people with those skills that understand that make it a routine part of the project. So I still see that as a significant risk. Scale is a big problem here. It's hard for people to get their head around a project in its entirety. So kind of developing approaches that enable people to understand what they're doing as part of this project to deliver the outcome is really a really critical softer thing. And again, we haven't got a complete handle on that yet. It's still emerging techniques in the infrastructure sector. I think probably in other sectors they've been doing systems engineering or these system approaches a lot longer, and perhaps they do it better. But in infrastructure, we still have quite a siloed mentality. I think we're getting over it. And as you saw with all of those reports, it's not as if it's not recognised. It is recognised, but there's a long road to get to that level of capability.
Thank you. Right, we've got a few more questions coming. So the next question then is: you've said that systems thinking goes as far back to the Greeks, and Apollo projects used systems thinking to get man on the moon. So why in 2018 did Crossrail so badly underestimate their system? So I think you said that you perhaps weren't direct. Why do you think that is for Crossrail?
It probably wasn't high enough on the agenda. I mean, I could turn it around and ask a set of questions. Did the leadership team there ask the right questions about systems? Were they asking those questions? Did they have the right information in terms of risks coming up to them as the project was transitioning from the civil engineering element, which I don't want to underplay at all, because that is also hugely complicated. And as I showed with the example with the Boston Big Dig, it's an immensely complicated thing to do. And naturally, the eyes will have been on that element. But as they were transitioning into the systems phase of the project, did they transition the team? Did they move from a civil team to a systems-oriented team? Did they have the operators on board early enough? Were the operators part of that team? Were they guiding where the system needs to get to? Did they push down the responsibility of system integration too far into the supply chain? Did they expect their supply chain just to deliver an integrated system? Did the client organization take accountability for leading systems integration? Were they acting as the system integrator? So all these questions that I would have around Crossrail, but it's much easier said than done. I mean, I've presented quite a simple process here, but we are talking about billions of pounds of spend here, tens of thousands of people working on these projects. I don't want to underestimate or diminish the scale of complexity we're talking about here. It is an incredibly difficult thing to do. If you look at the literature on major project delivery, and there's quite a lot published about it, you'll see that infrastructure delivery is difficult all around the world. This is not just a UK or Australia thing, and it goes across all infrastructure sectors as well. So delivering infrastructure projects to time and budget and the expected outcomes and benefits is a known problem. It's global, and lots of people do lots of research into how we can improve it. So it's not easy.
Okay, thank you. Thank you. A couple more questions have come in here. So next one from Thomas Moore. How do you see the challenge of obsolescence? Today's state-of-the-art is all too quickly obsolete. How do you manage modern systems with older systems?
That challenge happens on railways quite often, actually. So we also always have this problem of integrating legacy with new, and we could probably do it a lot better. I think there's a few things to think about. One is kind of how far ahead can you really plan, right? So delivering an infrastructure project might go on for a decade, it might go on for longer. So when you're specifying your initial systems, what do? Do you specify it for today, or do you specify it for a change that might be coming in the future? And GSMR is a good example in railway, where we know the obsolescence is coming, but we don't have a solution on the other side of that. So what do we do? Well, we don't have much option. But you can specify open systems that can interact and interface in different ways. You can design systems with easily replaceable units, so you can plug and play. But I think the reality is that this infrastructure is designed and invested in to last. The systems are probably invested in to last about 40 or 50 years. The civil, even longer than that, 100 years. So what essentially happens is that when the operator comes on board, they find themselves with this problem or this opportunity, and if it's been designed well, then in the future of this infrastructure, they'll be able to keep investing in it and upgrading to the necessary available technology at the time. So it's maybe about, I don't know if I answered the question there, probably, but I think it's kind of taking this longer term view.
Okay, thank you. Next question from Ahmad Udin. Often components are owned and not systems, which lead to lack of clear functional breakdown structure and interface contracts. What's your recommendation on this?
Well, that's a good question, right? So I talked in the presentation about the different life cycles and different sectors having their different life cycles for a good reason. So all of these assets and products, once you start looking at the supply chain, you start realizing that actually they're clustered into really quite small specialist groupings. So if you're working in building services domain, actually it's not really building services. It's actually lift escalators and alarm systems. There's lots of subsystems with specialist delivery organizations. And so we have to think about assets. Our supply chain and manufacturers are set up around assets. So that gives us a big problem. Because how do we bring all these assets together to deliver some functional output? And this is really at the nub of where systems engineering comes into things. At that top level, as the client, you have to do that functional analysis. You have to figure out what is it that you want this system to do. what functions does it need to perform? And you need to figure that out quite early in the process. And not only do you need to do it for the core functionality, you need to do it for degraded and failure modes as well. How is this functionality, what happens when the system fails, and how do those assets support that? And those functional requirements have to become part of the specification. But that's not enough either, because actually these assets need to work together. So not only do you need functional requirements at your asset level, but actually interfaces that enable those functions to work together. And all of that needs to be described in contracts so that you can get that collaboration between those different asset groups to deliver some kind of output functionality. And again, quite difficult things to do. Our normal contracting methods are not easily set up to do that type of integration.
Thank you. Thank you. Next question. What are some of the biggest challenges to supporting systems thinking and systems engineering within the industry, and where do these provide us the greatest opportunity?
Well, I think that the opportunity is really considerable. And I'm thinking beyond railways here and wider infrastructure and other types of systems. The opportunity is significant, profound even, because we're living in a world where we have got some really quite big problems to deal with, and many of those problems have come from the systems that we've created. And I think there is no going back. There's no going backwards now. So we've got to develop new systems that will help not make the problems worse, but also help solve those problems. And making best use of systems that we have is a key part of that. Designing new systems and new ways of working is a key part of that. Having engineers that can think about those systems and think at that system level using systems techniques. And I didn't really talk about systems techniques today, but there are a lot of systems thinking skills and techniques that you can use to help devise solutions to these problems or opportunities as well. And how do we get more of that into our project and into what we do? It's educating people. So I never learned. I did a mechanical engineering degree. I never learned systems engineering in my mechanical engineering degree. I learned about that when I joined the world of work, and I just happened to be in a project where someone was doing systems engineering, and I thought, oh, that's interesting. I'll go in that direction. So it's not really. There are degrees in systems engineering, by the way, so we are producing a good cadre of people coming out of university that can do systems engineering, but I don't see a lot of it in the traditional engineering disciplines, so mechanical, electrical, civil, etc. They don't learn about systems engineering so much, is my perception, and I might be wrong because they might have evolved in recent times. But a core part of it is education, and I think the other thing is people in leadership positions on these projects, especially at the top levels, they need to be systems thinkers as well. Because if they're systems thinkers, that culture will filter down the organisation.
Thank you. Thanks. Right, time for the last question here, which is, let's see, this one. Model-based system engineering is now becoming trending in the world, and some rail projects in the UK are beginning to adopt it. How do we use MBSE approach in rail industry?
Well, we must do it. Is my answer to that. It has been something that has been in and around the industry for quite a long time, certainly more than 10 years, probably longer than that. I've seen it used successfully on a couple of projects. East London Line, where I was not involved, used a type of model-based systems engineering to do their insurance, and that was very successful. I briefly mentioned digital engineering in the presentation. You might call that BIM. It's been called BIM for quite a while. But to do good digital engineering, I think we've got to move to that model-based systems engineering approach. So organising of the information and having the digital tools, be they CAD or specification tools or interface management tools that work within that model, I think is really quite important and will be at the heart of how we do systems engineering in the future. I think it's quite a difficult place to get to. Kind of developing that approach can be quite stifling for people as well. But I do think it's a very vital model-based systems engineering approach, if it's done in the right way and integrated with how the project works, and not just something that's done in the corner by the systems engineers, is a really good direction to go in, I think.
Fantastic. Thank you, Nasser, and thank you for answering all of those questions that the attendees have put to you. I'd just like to hand over to Prasad Behave, who's going to do the vote of thanks. Prasad.
Okay, thank you, Matthew. On behalf of IMechE Railway Division Southwest Region, it's my particular honor to thank our speaker today, Mr. Nasser Majothi, for dedicating his time and energy in helping us understand the system integration and system engineering. I should say it's a great follow-on from our IMechE chairman's address previously, where he explained both the complexity and the complicated nature of railway as a system. Nasser, you rightly highlighted the systems approach for navigating through complexity on mega projects, especially within the context of system of systems. And also you highlighted some key lessons, especially having a culture of system integration and leadership that understands integration, of course, with accountability and understanding of the key risks, especially technology risks and challenges. It was particularly interesting to know that excluding civils, which form about 80% of costs, most of the risks lie in the 20% of the other systems. So that was a very interesting aspect that you highlighted. You also brought out different approaches in terms of navigating through this complex system, especially in thinking as teams, having open dialogues, being agile, in controlling what you can, visualizing, having a route map, but especially, having a human-centered approach towards system integration. Finally, in a traditional way, I'd like to extend a round of applause on behalf of all the members today. In the traditional way, I'll clap on behalf of them. And I'd like to hand over to Mick James, who'll present some of the proceedings for the rest of the year. Mick, over to you.
Thank you very much. Thank you, Prasad. And firstly, I need to apologise to everybody. The next event, which we'd intended to run, would have been on the 10th of November. That event has sadly been cancelled. So the history of London Underground will now, hopefully, we'll reprise that again in a year's time. But for your information, our next event now is Tuesday, the 15th of December, which is an update on the progress of the P2 locomotive. Graham Nicholas from that project will give us an update. And we look forward to seeing you, as many of you there. in these days of virtual meetings, you are, of course, absolutely free to go to any centres meeting, and those are all noted on the IMechE website. If you go to events, you'll see there's a whole series of events that you can actually join. But we hope we will see you, even if it's only virtually, in December. It's at this point that I would normally offer you an invite to join us in the Glue Pot, which for non-Swindon residents is a public house in the Railway Village in Swindon, opposite the Mechanics Institute, which is the sort of traditional home of all institutions. Sadly, we can't do that, so please have a drink at home, and wish you good evening, everybody.
Thank you for that, Mick, and thanks again to Nasser, and wish you all a good evening. Thank you and goodbye.